Hi kids, this is Ms. Nichols, and this video is on the wave equation, which is our last equation of the year, and all the relationships between the wave variables that make up this powerful equation. The essential question today is, what are the relationships between the waves variables, and how do we reflect them together in an equation? So first, a quick reminder of the variables and what they depend on. The independent variables that we have learned about are the velocity, and the velocity is independent because it depends entirely on the medium that the wave is moving through. The frequency of the wave is independent. That depends on the wave source, so the thing that's doing the jiggling, whatever the wave is being caused by. And the amplitude is also dependent on the wave source. It's the energy provided in those jiggles, so that is also independent. The dependent variable that this equation is all about then is the wavelength. And the wavelength is going to depend on the frequency of the wave and also the material that it's moving through. Note that the wavelength does not depend on the amplitude of the wave, so changing the amplitude won't have any effect on the wavelength. The new equation that we're going to derive in a few minutes reflects the relationships that we just talked about. Okay, so if we were in class, we would do a bunch of demos to let you guys kind of figure out these relationships on your own, but they're pretty intuitive, and you can actually do a demo right there on your paper. So try this. Put your pencil down on your paper and start just jiggling it up and down, straight up and down for a second, just to kind of get the flow of things. And then start pulling the paper sideways, and you should be drawing a nice wave on your paper as you pull. One wavelength of this wave is going to be the distance between two crests. So you can go ahead and label that right on your paper. Label it lambda for one wavelength. Now, underneath your first right wave, you're going to do the same thing. And so the trick is pulling the paper at the same speed. But this time the difference is you're going to be jiggling your hand much faster. So like a 2 Hertz wave. So you got your paper, you're drawing on it like this, and you're still going to pull at the same speed. Okay? And go ahead and label one wavelength of the second wave that you made on your paper. Now, if you did this right, you should end up with a diagram that looks kind of like the one that I have there on the screen, where you have the longer wavelength on the top with the low frequency jiggling, and the shorter wavelength on the bottom where you were doing your high frequency wave. So if you think about this relationship here, the slower or the smaller the frequency, the bigger the wavelength became, or the bigger the frequency, the smaller the wavelength became. Hopefully that is bringing up some memories for you about these relationships. So if you thought about it, the relationship between frequency and wavelength must be an inverse relationship. We just saw that. The smaller the frequency, the bigger the wavelength, and the higher the frequency, the smaller the wavelength. What this means in a practical sense is that the faster the wave source is jiggling, the closer together the waves are. And you've seen this in your life. If you're in a swimming pool and you're kicking your feet really fast, the waves are really close as they move away. If you are holding onto one end of a slinky and jiggling very slowly, it's going to make really big, long wavelengths. So that should be a logical, intuitive relationship for you. Okay, I have a second little activity for you to do to figure out the second wave relationship. Grab your pencil again on your paper and just jiggle with a constant 1 Hertz frequency. And you're going to keep on doing the same frequency. Try not to speed up or slow down because we're not changing the frequency this time. This time what we're going to be changing is the velocity. So we'll represent that by pulling the paper slowly and then speeding up. So you're drawing on your paper and you pull slowly and then gradually pull faster and faster and faster until you're pulling fast at the very end of the page. If you label your paper, you'll notice that if you label one wavelength when the wave is moving slow on one side and then a wavelength where it's moving fast on the other side, those wavelengths are really different from each other. It should hopefully look like the drawing that I've kind of shown on the screen there, where you have a lower velocity at the beginning, and that is represented by a small wavelength. And on the other end, when the medium was moving really fast, we have a higher velocity, and we've got a much larger wavelength as well. This can also be represented by a relationship between these two variables, the velocity and the wavelength. And of course, you have seen that there's a linear relationship between velocity and wavelength. So when we had a low velocity, that made a small wavelength. And when we had a high velocity, that made a much larger wavelength. In the real world, of course, velocity doesn't change that way, the way it kind of sped up over time, because the velocity depends on the medium. So what it means kind of in a practical sense is that when a wave goes from one medium into another, what happens is instantly the velocity of that wave changes, and that causes the wavelength of that wave to change as well. So for example, if you're yelling at the water, when the sound wave from your mouth, it's moving through the air with a constant wavelength because it's in one medium. When it hits that boundary and goes into the water, it speeds up, and that means the wavelength is also going to get larger. And a note about that, interestingly, the frequency or the pitch of the sound doesn't change, right? The frequency is dependent on the wave source. So frequency and volume don't change, but when that medium goes from one medium, when the wave goes from one medium into the other, the wavelength does change. So those are the only two relationships that go into this super important equation called the wave equation. And if you wouldn't mind pausing the video for a second, you should be able to derive the equation. We've got the inverse relationship between wavelength and frequency, and a linear relationship between wavelength and velocity. You can smush them together into a new equation. Hopefully you remember how to do this. And the answer is wavelength equals velocity divided by frequency. Put a big box around that equation. It's a super important one that we're going to be using for the rest of the year. I want to run you through a couple sample problems just to give you some practice on this. And in class, we do a whole lot more of these, so these are really important for you to do and follow along. A rock star sings a 50 hertz frequency low note at a concert. The speed of sound in air is 340 meters every second. What is the wavelength of this sound wave? This is a level 3 problem because I'm pretty straightforward. I'm telling you two pieces of information and asking you to use the equation to calculate the third. First thing I would do is make a know-want list. And I know the frequency is 50 hertz. It tells you that in the first line. I also know the velocity is 340 meters every second. It tells you that in the second line. And what I want is lambda, which is the wavelength of the sound wave. The next thing to do is to identify your equation and then plug in your values and solve. So the equation is the wave equation, which we've just derived a minute ago. When you plug in the values, you'll look like lambda equals 340 divided by 50. And from this point, you just put those into your calculator and make sure you get your units on the end. So 340 divided by 50 gives you a wavelength of 6.8 meters. So interesting, right? Those sound waves coming out of that rock star's mouth are actually 7 meters long. They're pretty big, long things. You probably think of sound as little, but those low-pitched noises actually have a really big wavelength. So that's a realistic value that would be true for a rock star singing a pretty low-pitched note. So in addition to asking you guys to do some calculations with the wave equation, we'll also ask you to be able to explain things conceptually and talk about how the wave variables impact each other with relationships. If the rock star, for example, triples the frequency of the sound he was singing and halves the amplitude, we could ask you which wave variables would be changing and which ones would not, and how that would impact the sound of the wave you'd be hearing. So when the frequency is tripling, by itself, that tells me that we're going to be hearing a higher pitch sound. Higher frequency sounds sound higher to the human ear. The velocity of the wave actually doesn't change because velocity depends on the medium. Since this rock star is presumably still singing in air, the speed of the wave, no matter what its frequency is basically going to be the same. And our ears couldn't detect it even if it did change. The wavelength of the sound has an inverse relationship with frequency, as we just figured out a minute ago. So when the frequency goes up by triple, the wavelength actually goes down, and the wave becomes smaller by about 2/3. It becomes smaller to 1/3 what it was originally. And the last wave variable is the amplitude, and we mentioned that he was halving the amplitude of the sound he was singing. Amplitude is independent, but it controls the volume of the sound. So when he halves the amplitude, we're going to hear this as a much quieter sound. So this is a higher pitched but quieter sound. I wanted to give you a sample of the level 4 kind of problem as well, so you could see how we can make this a little bit more complicated. A swimmer is creating waves by kicking in a pool. At any moment in time, there are 6.5 complete wave cycles. So that's like 6 full waves and then just 1 extra crest or 1 extra trough in the 50-meter long pool. If it takes one of those wave pulses 7 seconds to go from one end of the pool to the other, the question is how many times was that swimmer kicking their feet every minute to generate this wave? So we got a lot going on in this thing. But we're still going to do the same old start off with a know and want list. It's just that we have to put a little bit more thought into what goes into this list. So for example, if we read that first sentence, at any moment there are 6.5 complete wave cycles in the 50-meter long pool. It's not saying it really clear, but cycles in a space, how many waves fit in a space, is the wavelength of the wave. So I know that in that 50-meter space, there's 6.5 complete waves. So you can picture how long each wave would have to be. Each wave would have to be 50 meters divided by 6.5. That means each one is 7.7 meters long when you plug that into your calculator. So my know list would start with wavelength equals 7.7 meters. The second sentence says it takes the wave 7 seconds to go from one end of the pool to the other. This is our old friend velocity, right? How fast something is moving. But you have to do a little bit of work to calculate velocity. Remember that velocity is the distance covered every second. So in this case, we know it goes 50 meters in 7 seconds. So when you put that into your calculator, you actually get a velocity of 7.1 meters every second. And the last thing is the want. We're asking for the frequency, which is a number of cycles every something. But a little bit of a note here, we're asking for cycles per minute. The equation is going to give you cycles per second. So we're going to have a conversion at the very end to get from cycles per second into cycles per minute. So there's your setup. To continue the solution, we're going to be using the same wave equation. That's really the most powerful equation of this unit. But when we set up our problem, when you plug in, it looks like this: 7.7 equals 7.1 over f. Remember, when you have that variable on the bottom that you need to solve for, the easiest way to do is to set up a cross multiplication. So we set it up 7.7 over 1 equals 7.1 over f, because we have to get the f all by itself, and this is really the best way to do that. So then you multiply together the numbers on the on the edges of the cross. So the 7.7 times the f and the 7.1 times 1. And you write a new equation that looks like this. 7.7 times f equals 7.1 times 1. And then I start simplifying. So the goal is to get the f all alone. So the thing that was preventing the f from being all alone was the 7.7. So I'm going to divide both sides by 7.7. So that 7.7 cancels out on that one side and leaves the f all alone. And when you're done, you get this f equals 0.93, and your units are hertz, which is cycles every second. So the very last step is to convert our cycles per second into cycles per minute, and we'll use a conversion factor like we learned how to do earlier this year. So 0.93 cycles for every 1 second, and then the conversion factor is 60 seconds equals 1 minute. This way we can cancel out that second on the top and the bottom, and I'm left with a solution of 55.8 cycles every minute. So this is a level 4 problem that involves some more complicated variables from the beginning, and then cross multiplication, which is a little bit of a trickier math concept, and then also a conversion at the end. Okay, so let's revisit the essential question, which is, what are the relationships between the waves variables? I know this was a little bit of a more mathy thing, but there's also, a lot of concepts in there as well for you guys to work on. And this is the last big equation of the year. So if you need help, please make sure you contact your teacher during their office hours, and rewatch the video if necessary. Thanks.